Let B be the set of rectangular prisms that have surface area 54 and volume 23. Let R be the radius of the smallest sphere that can contain every element of B. What is the value of R squared? So, in order to do this problem, we need to first imagine our one rectangular prism inside B. So we have our rectangular prism here. Suppose it has side lengths x, y, and z. Then the volume condition is equivalent to xyz is equal to 23, and the surface area condition is equivalent to xy plus yz plus zx all times 2 is equal to 54. And we can divide both sides by 2 to make things simpler to get that xy plus yz plus zx is equal to 27. And we want to minimize the value of x squared plus y squared plus z squared over 4. So the minimum value of this is equal to r squared. And after a bit of rearranging, we end up getting minimum of x squared plus y squared plus z squared is equal to 4r squared. And the reason why I'm dividing this by 4 is because we want half of the length of the diagonal. And the length of the diagonal is square root x squared plus y squared plus z squared. So half of it squared is this divided by 4. And since xy plus yz plus zx is fixed, we are motivated to add twice of it to x squared plus y squared plus z squared. And then we end up getting minimum of x squared plus y squared plus z squared plus 2xy plus 2yz plus 2zx is equal to 4r squared plus 54. And therefore, the minimum value of x plus y plus z squared is equal to 4r squared plus 54. So the minimum value of x plus y plus z is equal to square root of 4r squared plus 54. Now we've reduced the problem to minimizing x plus y plus z equals n, given these conditions. And by Vieta's formulas, this means that x, y, and z are roots of the cubic s cubed minus ns squared plus 27s minus 23 is equal to 0. If n is too small, then this cubic only has one root because it only intersects the x-axis at most once. And if n is too large, then this cubic has 3 distinct real roots. So we want n to be just right in between. Like, it doesn't have quite 3 distinct real roots, but it doesn't have one distinct real root either. So let's make it have 2 real roots. That is, we assume that 2 of these roots are equal. So let's, without loss of generality, assume x and y are equal. Then these above equations reduce to x squared plus 2xz is equal to 27, and x squared z is equal to 23. This last equation implies z is equal to 23 over x squared. And plugging into this equation here, we get x squared plus 46 over x is equal to 27. And multiplying both sides by x and simplifying, we get x cubed minus 27x plus 46 is equal to 0. This is a cubic in x with integer coefficients, so we can only pray that there is a rational solution. And that rational solution, by the rational root theorem, must divide 46. And it must be, we're trying to make it positive, ideally, because x, y, and z are greater than 0. So let's try out the factors of 46 that are positive. So for 1, we just have 1 minus 27 plus 46, which is 20. That's not 0. For 2, we have 8 minus 54 plus 46, which miraculously happens to be 0. And therefore, x is equal to 2. And so is y. So x equals y is equal to 2. And since x, y, z is equal to 23, z is equal to 23 over 4. Since this minimizes x plus y plus z, this will minimize the value of r squared. And finally, the value of r squared is square root 2 squared plus 2 squared plus 23 over 4th all squared all over 2, which is square root 1 squared plus 1 squared plus 529 over 64, which is equal to the square root of 657 over 64. And therefore, the value of r squared is 657 over 64. And we have solved an AIME problem number 15. So thank you so much for watching this video. Please subscribe if you'd like to see more.